So thrust 2 goals, we're basically an analytics team. If you want to look at it from the point of view of the types of fundamental capabilities we're trying to build in terms of modeling and building algorithms to effectively perform anomaly detection for diversions or other types of anomalous activity localization. Fundamental physics modeling, radiation detectors, so new types of algorithms and models to improve the efficiency, sensitivity, resolution of radiation detectors, and then image processing and signal processing methods for gathering together and integrating diverse data with massive amounts of objects and instances. So I'm going to discuss a little bit on each one of these as I go through my slides. But the thing to remember is that we are an analytics team, but we're very much looking for interactions with the labs so that we can transition some of these methodologies, some of which have only been able to demonstrate in simulation. Others have been demonstrated experimentally, as you will see. So this is sort of just a cartoon picture that allows me to describe sort of where we are located in the spectrum of the CVT. So of course, one of the principal objectives of the safeguards is timely detection and early detection of diversions and other anomalies, so that one can go towards deterrence, interdiction, and policy. In this type of problem, of course, we have a nuclear fuel cycle, or maybe a network of fuel cycles, which you'll see later on. We have some modeling that we've introduced for detecting divergence among networks that might be different nation states, or a given nation state with many different nuclear fuel cycle cooperative productions. So weapons development programs, of course, are what we're trying to detect in terms of undeclared facilities or diversions of nuclear materials. And these diversions we're looking at from the point of view of many different types of modalities where we can detect different types of diversionary activities. And one of them, which I'll talk about in a minute, involves looking at patterns of interactions between these particular components of the nuclear fuel cycle or different fuel cycles, interactions that could be, for example, delivery or shipment of nuclear materials, and which perhaps there might be some diversion where if you observe at an enrichment plant, for example, as indicated on the slide, the ingress and egress of deliveries and shipments by looking using, say, satellite imaging or some other type of remote sensing, the number of vehicles per unit time and coming into the facility and going out of the facility, you may be able to detect some slight differences of those. So even if you don't observe the vehicle that goes out under cover to another site, you can infer that statistically through correlation of these measurements with other types of measurements. And so one of them being power or utilities usage. So that's one aspect of the sort of paradigm we're looking at for diversion detection, developing algorithms and models to detect interactions and interaction patterns that might be anomalous and indicate perhaps a lack of compliance with agreements. Another area that we're looking at, which is related, is emission monitoring, and this involves developing models for things like plumes of chemical releases or radionuclide releases into the atmosphere or into water bodies, and looking at ways to both optimize with limited sensing resources where we place resources in order to observe, say, suspicious releases of krypton or iodine, say, in an enrichment facility or reprocessing facility, and also techniques for getting much more accurate ability to discriminate between what is normal for a enrichment facility, let's say, in terms of their chemical release patterns, and what might be abnormal that might indicate some sort of activity that has not been typical in the past. So finally, another aspect that we're focusing on is cyber attack detection. Of course, there's been a lot of news over the past 3 or 4 years on attacks, intrusions on nuclear facilities, and those could be, of course, detected using methods, network detection, classic types of administrative internet or firewall types of methods. But here it's a very specific type of model that is related to the programmable logic controller technology that controls valves and centrifuges and so forth, as in the Stuxnet problem that happened, problem for a certain country. And then in situ radiation detection, where you look at radiation detectors that are on site, and we try to improve the detection efficiency. Okay, so this just shows one of the areas that we've been looking at, and we presented this work. There's one of my students, Elizabeth Howe, who's here, on delivery shipment network monitoring. So just this shows a case where you have an actual network, which is denoted ground truth up here, well, a network of origin-destination pairs, right, of shipments going from one facility to another facility. The little boxes denote observations of en route shipments. So you track a vehicle while it goes from one facility to the next. Obviously, very difficult, resource inefficient. But in practice, of course, you don't have complete observations, so you're stuck with observations on the right here, which is just an incomplete view of this network of origin-destination pairs. And so what can you do in terms of being able to detect or reconstruct certain anomalous patterns in traffic? Well, we introduced a method of network tomography, which uses a gamma Poisson model, for those of you who are interested in algorithms, to do both anomaly detection and tomography. And we show in the bottom that you get much improved performance relative to a standard least squares type of algorithm approach in yellow here as a function of the percent of edges known in the network. The rate recovery error is much lower with the proposed algorithm. And the green surface here denotes the computational complexity as a function of the length of time of the observation and the percent of edges known, and there also we do much better with this type of model-based approach. Taking this to another dimension, the same delivery shipment monitoring, we have another paper that we recently presented at the same workshop in September on quickest change detection. So incorporating a penalty for delays in the time to detect an anomaly, and this is work that we have in collaboration with the University of Wisconsin, Paul Wilson, who is also with the CVT, and we're using quickest detection methods to detect HEU changes or diversions based on subtle changes in power consumption or in shipment statistics, Poisson-like shipment statistics, where you're observing shipments to several types of customers. And so this just shows that our proposed algorithm does a much better job as a function of the false alarm rate in giving us a very fast and rapid detection of anomalies that might occur over this, this 2,000 measurement sequence seconds, which is the horizontal axis on these two shipment and power curves, where at 1,000 units, we get a 1% change in the amount of power and in the Poisson statistics of shipments to one of the customers. So you can't see the difference. If I'd blown this up, you wouldn't be able to see much difference either, but our algorithm is able to pick it out because it uses this Bayesian Q-sum test with multimodal integration methodology. Another method that we've been looking at, or sort of area we've been looking at, again, is this mission monitoring. And for this, there are really two approaches that our team has been taking. One of them by a student of mine, Elizabeth Howe, again, who's here, who has a poster on this, so I won't dwell on this. You can go to the poster to see more. It's simply using a shallow water model for detecting atmospheric or water releases and tracking them over time and looking for anomalies in terms of rates of release over time in a Bayesian context, so that you can actually assign probabilities to your anomalous observations. If they have a very low probability of being consistent with your previous observations as predicted by the model, in this case we use an ensemble Kalman filter, which is a non-parametric version, non-parametric Bayes version of the standard Kalman filter, well then you know that you have an anomaly with high probability. Another aspect of this is work by, at MIT, John Fisher, who has been working with the Pacific and Northwest, and the technical challenge here is how to actually schedule sensing. If you have an airborne sensor that flies over a region where there may be multiple emissions, either atmospheric or other domain, how do you optimally plan the flight path or optimally plan your sensing? And he takes again, a Bayesian information planning approach with a graphical model plus transport physics, a geometric flow model based on an ODE that allows him to introduce, and I have a movie here that's not working, as you can see, introduce this transport wind or current velocity, which changes according to some complex, perhaps Navier-Stokes physical model, but modeled through a geometric approach, which obeys a multi-resolution and multi-scale acceleration in terms of computation. So you can talk to John here. He's in the audience if you're interested in more details on this active localization of emissions. Another area that's also covered in a poster that I won't cover in much detail is from the Duke group, who are looking at incorporating deep learning algorithms for better being able to classify particular types of anomalous behaviors in images, satellite images. For example, if you are looking at satellite images of deliveries and shipments out of a particular facility, as in our previous project, then having these types of very efficient and high performance deep learning approaches to extract information about whether there are anomalies in the patterns of shipments by looking at segmenting out moving vehicles or trucks or dismounts or what have you from each one of these areas. I won't say much more about it other than they've developed a method which is a Bayesian method of deep learning that allows them to improve performance demonstratably over the many classic image databases, including ImageNet, achieving the best accuracy yet in terms of classification performance. So highly relevant to our projects in detection of remote detection of emissions and also traffic anomalies. Cyber intrusion detection, we have a talk coming right after mine, which will go into much more detail, but clearly this is a problem that has been of quite a bit of interest, and we introduced this method of anomaly detection for cyber intrusions that goes beyond just simple firewalls and simple univariate pattern analysis. We use a graph centrality, multi-centrality approach, which will be explained in the next talk, to obtain much more effective anomaly detection, cyber intrusion and attack performance than has been achieved in the past. Finally, in the fundamental physics modeling area, with work, this is work that's joint with Sarah Posey's group, Angela DeFulvio. We've been looking at improving the methods to basically estimate concentrations of neutron and gamma photon in fissile materials as a way to avoid complicated coincidence type detection schemes. We use spectral methods with a Bayesian approach. Lots of our approaches here are Bayesian, and that leads to significant performance advantages, as you will see if you look at the poster. But one big advantage here, and I'll just show this picture over here on the top right, is that what you have in blue and what you have in red is the separation of gamma photons on top and neutrons on the bottom on a per pulse basis. This is a Californium 252 source with the organic scintillator array in Sarah's lab. And each one of these dots here corresponds to a particular position in the principal components area for PCA on the pulse energy spectrum. And what the colors denote is it's a continuous color scale, the posterior probability of being a neutron, right? So you can't see it too well from here, but there's actually a color gradation near the threshold line that separates the two types of pulses. So you have a quantitative way with this Bayesian approach to assign a likelihood that a particular pulse has come from a neutron or a gamma photon phenomenon. All right, so in conclusion, we're making progress on the data analysis component with lots of different collaborative efforts. 6 national laboratories. We place our students in many of these laboratories contexts where they can get specific guidance and information on making their research as relevant as possible to the CVT mission. And these are the other presentations. And that's really concludes what I have to say today.
If you use betweenness, then you are more interested in the shortest path of a node to other nodes. Also, closeness will be something related to the hop distance to other nodes. Then eigenvector centrality is something like a Google page.